So we are pretty much finished with Unit 10, so we're going to do like a review unit because the semester is going to be ending soon. We actually don't have time to complete Unit 11, which is on probability and statistics, so we're just going to be circling back to exponential growth and decay because we didn't do particularly well on the test from that before the semester ended, so wanted to go over some of this again. Now, I gave you two topics to do on exponential growth in the previous Delta Maths. One was using the exponential growth and decay formula. The other one was on doubling and halving formulas. So these were two formulas that we would have seen in the previous two Delta Math assignments. It could have also been a half if we were doing the halving assignment, but let's take a look at today's work. Today our goal is to talk about compounding versions of exponential growth and decay. So it says, how do we solve problems involving exponential growth and decay? Our do now assignment is which of the following are exponential growth and which are decay, and to state the starting value and the scale factor. So I'm just going to pick the last example here just to go over one of them. You can do the other two on your own when you submit the assignment. So we're looking at this table. Our first value is 0, 4. This is kind of like a geometric sequence because they're exponential. So the starting value is 4, so that's like A0 really. And the multiplier is our scale factor, and that in this case is 3. So this exponential equation is y equals 4 times 3 to the x power. Now, that would be in this form, where A is our starting value, which is 4, and B is our scale factor, which is what we multiply by to get from one number to the next. So as we multiply from 4 to 12, we multiply by 3. And we do that again to get from 12 to 36. Now this can be rewritten in a rate form, which is y equals 4 times 1, either plus or minus a number. But to get to 3, it has to be 1 plus 2. 2 represents 200%. So this is a growth, because of the plus, of 200%. You can try and do part the first and second examples when you submit your assignment on your own. Next, we're given 6 problems here to do, and it says, is the problem growth or decay, and by what percentage? So this first one, this number 2 here, if we look at it, we can see a plus here, which means this number is bigger than 1. If the number is bigger than 1, it is a growth. If it is smaller than 1, it is a decay. So this would be a exponential growth function, where you start with 200, and it increases by 6%. Now 0.6 is 6%, and 0.6 would be 60%. So that's this is the tenths place, and this is the hundredths place. So we got to be careful about positioning of the values. Number 6, on the other hand, is a little bit of a trickier problem. You might be tempted, this is definitely a decay because this number is less than 1. Like this one's less than 1 as well, problem number 3, but problem number 6 is also decay. But this one is written where the two numbers are combined already, just like in the problem in the do now assignment, where the scale factor was actually 3, but the rate of increase was 200%. This is actually equal to 1 minus 0.08. This is actually a decay of 8%. This is a decay of 8%. All right, so I'll let you try the remaining examples. So we've done problems 2 and problem 6. You're going to have to try and answer problems 1, 3, 4, and 5 in this section. Next, we're going to take a look at some word problems. These are similar to the ones you would have done on Delta Math. So I actually won't be spending too much time on them. I'm just going to do problems 8 and 11 on this side, and then we'll take a look at the back. So problem 8. It says a town has a population of 6,000 and grows by 2.5% every year. To the nearest tenth of a year, how long will it be until the population reaches 100,000? So this is an exponential function because it grows at a percentage every year. So we're going to write something in this form. Y equals A times 1 plus or minus r to the x power. we're told that we start with 6,000, so that means A is going to be 6,000. So 6,000 is our A value. We're growing at 2.5%, so this is going to be 1 plus. 2.5% would be written as 0.025. And we don't know the number of years. So, and this has to equal 10,000. So we're using the exponential growth function where we actually were aware of the starting value, the rate, and the ending value, but not the exponent. So I'm just going to go over how to find the exponent. Let me rewrite 10,000 since I seem to have left that as 0. So firstly, we're going to solve this using a logarithm. Pretty much any problem you solve for an exponent, you're going to be using a logarithm. So firstly, we're going to try and isolate the term with the exponent. So we're going to cancel out the 6,000 by dividing it from both sides. So these 3 zeros cancel out, and we have 10 over 6, which is approximately equal to 1.6 repeating, which is going to be equal to 1.025 to the x power. So that is this expression when combined. So the 1 and the 0.025 are going to combine into be 1.025. Now we're going to try and get the x by itself. So we can do a logarithm. Now I'm going to show you the way it is done on Delta Math, because I taught it differently in the classroom. We can put a log on both sides of these problems. So we're going to put log here. So this is log base 10. We can do ln, we can do any log base, it doesn't really matter. And then there's a log rule that says we can take an exponent and bring it down in front as a coefficient. So we're going to rewrite this as log of 1.6 repeating equals x log of 1.25. So the only thing we need to do to get the x by itself is to divide both sides by log 1.25. 0.25, excuse me. I left out the 0 again. So we're going to divide both sides by log of 1.025. And this is going to be our value in our calculator. So x is going to equal log of 1.6 repeating divided by log of 1.025. Now, this is mathematically equivalent to x is equal to log of base 1.025 of 1.6, which is what I showed you in the classroom. So this would be a similar method of solving. We're not going to use this. All right, so I'm just going to type this into a calculator, and we're going to see what value we get. Now, this problem tells us to round our answer to the nearest tenth of a year. So we're looking for something like 5.2 or something. So x equals calculator. So I'm going to be typing in log of I'm just going to type log of 1.66666. I'm just going to give the calculator enough sixes to know this is a repeating decimal. I'm going to close that. I'm going to press divided by log of 1.025 and press enter, and we get 20.687. So about 20.7 would be the nearest tenth. 20.68, and since we're going to the nearest seventh, this is going to round up. So x is approximately 20.7. So that means if we plug in 20.7 into the exponent of our original problem, we should get 10,000. All right, problem 7 is a little easier because you're solving for y in problem 7. Problem 9 you solve for y, problem 10 you solve for x again. And I wanted to take a look at number 11 because this is a little bit of the trickier types of problems that will be coming up on the Delta Math. So problem 11. This is a Regents problem. A student studying public policy created a model for the population of Detroit, where the population decreased by 25% over a decade, meaning in 10 years. He used this model. P, which is population, is equal to 714 times 0.75 D, where D is the number of decades after 2010. It says another student wanted to do this in years. So these multiple choice options might not look all that different, but you'll notice that all of them have a y in them, and that's because this is in years. So we have to somehow convert d into years. So the way we're going to do that is we're going to say the population is equal to 714 times 0.75. And now I need to have years here, but it needs to be something that makes sense. So it's not years. How many years does it take it for this decay to happen? So 0.75 is the same thing as 1 minus 0.25, which is why this is a 25% decay. So this is going to happen after 10 years. So when y equals 10, this will be the expression. So it's 714 times 0.75 y to the power of y to the divided by 10, meaning after 10 years, we'll have 1 decade and it'll have the same representation. But according to the problem, we don't want to have the over 10 in our solution. So what we're going to do is we're going to apply an exponent rule, and that exponent rule says that x to the ab is equal to x to the a to the b power. So what that means is we can bring this over 10 inside the parenthesis. So this is going to be p equals 714 times 0.75 to the power of 1/10 to the y power. And this expression is going to simplify to be one of those other rates. So currently we're looking at the decade rate. This will convert it to a yearly rate. So we're going to use our calculator and figure out which one is the correct one, if any of them. So we're going to write 0.75 to the power of 1 divided by 10, and that is 0.97. So apparently a decay of 25% per 10 years is the same thing as decreasing by about 2.9% every 1 year. So we're looking for 0.971, which is choice C. Okay. All right, so we're going to take a look at something slightly different now. So you can convert exponents in several ways. Now, the rest of the problems are based on the compound interest formula, which is very similar to the previous formula. So the formula we were using before is y is equal to a, the starting value, times 1 plus or minus r to the x power. This formula is very similar. So the a value is going to be the same thing as y. So these are the same. The p value is going to be the same thing as the a value in the other formula. R is still the rate. So that's here and here. The only difference is there's an additional value n. So the n value is the number of times that interest is compounded in a given year. So this is sort of like changing a yearly formula, because this is like 1x, into some other amount. So this is like 1x over 1. So if we're doing it for a different amount of times that things would be compounded in a year, we would actually use this formula, the compound interest formula. So if something is done monthly, it's going to be done 12 times. These are for your n values. Annually means once per year, so that's kind of the standard formula. Semi-annually is twice a year. Daily is 365 times in a year. Weekly is 52 times in a year. Bi-weekly means every other week, so 26 times in a year. There's also quarterly, which would be 4 times in a year. And continuously is infinitely many times, so at all points. So this one you can't plug in infinity because it's not a number, so there's a separate formula for that. It's p is equal to, not p, excuse me, a, the final amount, is going to be equal to the, what's the word for it? The principal amount or starting amount times e, which is a number on your calculator, to the RT power. So this formula is going to be equivalent to using the compound interest formula, but with the n value being infinity. All right, we're going to do problem 13 and 15. All right, so problem 13. Stella invested $30,000 into an account paying an interest rate of 3.5% compounded monthly. Important that we notice it's compounded monthly. Assuming no additional deposits or withdrawals are made, which all these problems are based on this being true, how much money to the nearest dollar? Actually, that's incorrect. I think this problem is supposed to say how many years would it take for Stella to have $50,000. So it should be how long to the nearest year. So this is an accident, so I'll know if you paid attention to that in the on the worksheet when you submit it, because this problem doesn't make sense to answer without answering for years. So to the nearest year, how long will it take for Stella to have $50,000? So that means we're taking A equals P times 1 plus R over N to the NT, where we know that the final amount of money we want to have is $50,000. And the starting amount was $30,000. It's happening monthly, which is 12 times. And what we don't know is T. So T is what we're going to be solving for. We're told that the interest rate is 3.5%. So this is 0.035. So we're going to solve this problem the same way we did earlier. We have 50,000 equals 30,000. I'm actually just going to simplify what's inside the parentheses. So this is going to be 1 plus, I'm going to do on my calculator, .035 divided by 12. And that means this is going to be 0.002916 repeating. Okay, to the 12t power. Okay, so now we're going to try and get, oh, I put an extra equal sign here by accident. This should not be here. This should be 30,000. All right, and the idea is to get the expression with the exponent by itself. So this 30,000 needs to cancel out, so we're going to divide that to the other side. When we do that, we're going to get 1.6 again. So that's 5 divided by 3 equals 1.002. Running out of space. Let me just move this over. We're going to get 1.6 repeating equals 1.0021. Oh, 9, excuse me. 9, 1, 6 repeating to the 12t power. All right, so now I'm going to do what we did in the previous problem on the word problem on the other side. I'm going to bring that 12 inside using the exponent rule so that the t is by itself. So I'm going to write 1.6 repeating equals, now I'm just going to take the 1.00291666666666666, raise that to the 12th power. So I'm bringing the 12 inside the exponent. And that gives us 1.035, 566. I'm running out of room, so I'm going to stop here. But as long as you're including enough decimals, your answer should get pretty accurate. All of this to the t power. Okay, so again, I just raised what was inside this parenthesis to the 12th power. So now we're just doing the same thing we did on the other side's problem. We're going to use a logarithm. So I'm going to put a log on both sides. So I'm going to put log here and log here. So, and I'm going to bring the t down in front. So we're going to get log of 1.6 repeating equals log of we're going to put an x in, we're going to bring the t down in front, so it's going to be a t. Then log of 1.03556, and then I'm going to divide the log to the other side here so that the t is by itself. So divide by log 1.03. I'm looking at the calculator for my numbers. I know my handwriting's getting kind of small here, 566. And we're going to get, so using a calculator, we're going to get t is equal to log of 1.6666666666666 divided by log of 1.0, whoops, left out the 0.033 5566. And we're going to get about 15.476. So to the nearest year, this would be 15 years. So it'll take Zoe 15 years to boost her. It'll take Stella 15 years to get approximately $50,000 into her account to the nearest year. If it was to the nearest tenth of a year, which I didn't really specify because I think I made a typo there, it would be 15.4 years. All right. Number 15 is going to be converting a problem into a different, we're going to do problem 15. So problem 15 says, is another Regents problem. I changed it from a multiple choice question to a different type of problem, and then the rest of these are going to be yours to try. So it says, on average, college seniors graduating in 2012 can compute their growing student loan debt using this function, where t is time in years. So we're asked to create an expression to do this using a daily rate. So in order to be daily, we need our problem to have the power become 365 to the t. So that's what we're going to do. So these are the most common problems that show up on the Regents. So in order to do that, we're going to take this problem. We're going to write 29,400 to the 1.038. And I'm going to let me move this over, get a little more room here. 68. I wrote 38. So 0.68. I'm going to write this as 365 over 365 power. And just like I was able to bring the 1/10 inside before, I can bring the top 365 to the outside of this parenthesis. So this will become, let me move this out of the way, 29,400 to the 1.068 to the 1 over 365 to the power of 365 t. All right, so now all I have to do is evaluate this expression here to get the daily interest rate. All right, so we're just going to calculate that using a calculator. So just going to open this. So we're going to do 1.068. If I could type the right thing, it would work out. 1.068 to the power of 1 divided by 365. So that's going to be 29,400. Running really low on space here. I'll write it over here. 29,400 to the 1.000182563 to the 365 t power. Now, this is the daily rate in a year, but we could also rewrite this as 29,400 to the 1 plus, because remember, this should be over 365. So that means I'm going to take this section of the expression, and I'm just going to multiply it by 365. So that's 0.000180256663 just looking at the calculator screen, and I'm multiplying that by 365, and that is 0.065793. So this is the, all this is to the power of 365t. So this is now written as a 6.5% daily interest rate, is the same thing as a 6.8% interest rate yearly. Now, a lot of these problems on the Regents are actually going to not actually change from this point to this point. So on the delta maths, they're probably going to stop here. But it could come up that they would ask you to go into this format. All right. So I want you to try the delta math problems on your own. I'll make an additional video if anyone has questions about any particular problem, but I would recommend you actually do the delta math assignments before you do